For today's lesson, we will be doing a question on exponential decay. So let's read the question. Cesium-137 decay can be modeled with the formula A of t equals A to the 0 power e to the power of k to the t. So this is an important formula, so let's highlight that. Where A of t represents the mass remaining in grams after t years. It's important, let's write that down. So we know that A of t equals the mass remaining. Okay, and this is going to be in grams, as it says here, and that's after t years. So t is the years. And A of 0 represents the initial mass. So A0 is the initial mass. A sample of 500 grams of cesium-137 takes approximately 60.34 years to decay to 125 grams. Use the sample with the given formula to determine the constant K to the nearest 1,000. Okay, so let's create a formula for that. So first, whenever we're doing exponential decay, we like to have exponents in our formula. We also need constants, and we also use the initial mass. So first, let's use the formula that they gave to us, which is, A of t equals A0 e to the kt. Okay, and now let's plug in what we know. So first, it says here that A of 0 represents the initial mass. And then after that, it says that there's a sample of 500 grams. Okay, we know that that is the initial mass. So let's plug in A of 0 equals 500 grams. Okay, we also know that it takes approximately 60.34 years to decay. So that can be written as t. T is 60.34 years. Lastly, we know that it takes that many years to decay 125 grams. So we can plug in 125 grams into the mass remaining, because that's how many grams we need after t years. So A of t is 125 grams. Okay, now that we have all of our information down, we can start plugging these numbers into our formula. Okay, so using A of t equals A0 e to the kt. Let's plug in 125 for A of t. A of 0 is 500. E, that's just a regular constant, so we can leave that there. So times E. K is also a constant, so we can leave that there. And then T is 60.34. Okay. So now that we do that, we can start to calculate. So first step is we can multiply 60.34 times K. That can just be 60.34K. We just want to rewrite that mathematically, make it look nicer, and write down the rest of our information. Okay, our next step is we can divide by 500, right, to get our E alone and our K alone. So when we divide by 500 on both sides, now we can put that into the calculator, which you can see on the right. So we did 125 divided by 500. Okay, and that gets us 0.25. So now we have 0.25 is equal to E 60 to the power of 60.34 K. Okay. Now our next step is we want to neutralize this E. So one way that we can do that is we can multiply them both by ln. Okay, so if we multiply the left side by ln, so ln to the 0.25, and then the right side by ln, so ln to the E 60.34. Okay, this cancels out the ln and the E. Right, so now we just have 60.34K. And then on the left side, we can we just have ln times 0.25. Okay, our next step is we want to isolate the variable k. So we can do that by dividing both sides by 60.34. Okay, when we do that, now we can isolate the k and put it on the left side, and on the top we can put ln times 0.25 and divide that by 60.34. Okay, next step is let's take out our calculators and multiply ln times 0.25. Okay, when we do that, we get negative 1.3 I'm going to go to the thousands place because that's what it's in the question. Okay, we take that number, divide that by 60.34, and we get an approximate value of negative 0.023. Okay, and that value is equal to k. So now, let's plug everything back into our original equation. Let's plug everything back into there. So first, we have a of t, because that's what we're trying to graph. A of t is going to equal to a of 0, which is 500, times e to the k, which is negative 0.023, times t. Okay, and this is our final equation that we will be using to graph. Okay, so now let's bring this equation up to the top. Okay, just so that way we know our equation and we can easily access it. Okay, now our next step is we want to graph a of t onto this graph here below from t equals 0 to t equals 150 years. Okay, so first, before we do that, we need to label our axes. So we know that our x-axis is t, which is years. So let's start with having a 0 here, 150 years here, and we're going to have a 50. Let's put that here, and a 100-year, put that there. A bit over more. Okay. And now for our a of t, that's just going to be determined by our calculations. So let's take out our calculator and start graphing. So the first part is we want to plug in our formula. We can do 500 times e to the negative 0.023, and we're going to times it by 0 first, t. Okay, and that answer we get 500. And let's not forget this is exponential decay, so 500 is likely going to be at the top of this graph. So we're going to put 500 up there. Okay, now we can continue graphing the rest of the t points into the exponential decay formula. So up next, I'm just going to switch out the 0 for a 50. And when I do that, I get 158. Okay, so that can be placed along the middle between 100 and 200. Go around here. Up next is 100 years. That gets me 50, a little bit over 50. Keep doing that. Okay, and the last one is 150 years. That gets you 15. Okay, now that we have all of our points, we can begin to graph. Okay, so now this is roughly what our exponential decay graph is going to look like. Notice how it's going down as the years go on, meaning that the cesium decay is going to lower based off how many years that pass. Now that we finish graphing, we can start with the second part of our question here. So the second part of our question reads, use a of t to calculate the average rate of change in grams per year from t equals 0 years to t equals 60 years to the nearest tenth. Explain what this value means in the given context. Okay, so we need to go from 60 years to 0 years. We need to figure out how to calculate that. So one formula that we can use to calculate the change in years here is we can do a of t 2 minus a of t1, and we're going to divide that by t2 minus t1. This will help us signify and separate which which numbers are years, which numbers are growth rates, which numbers are the first year, which numbers is the second year, so we can use this formula for that. Okay, now let's start to plug in what we know. So we're going to use t of 2 is 60, and t0 is 1. Okay, so we know a of 60 minus a0, and we're going to divide that by 60 minus 0. Okay, now we need to figure out what is a of 60, and what does a of 60 mean? Okay, so when you look at a of 60, we know that that means that it's for the years, and we know that we can plug in 60 for those years. We're going to plug that back into our original formula, a of t equals a0 times e to the kt, and instead of using a 0, a 50, or 100, whatever we have been using, we're going to use 60 instead. Okay, so we're going to plug that in for 60. So a of 60 equals 500, the initial value, e to the negative 0.023 times 60. Okay, and when we get that answer, when we plug that into the calculator, we get a value of 125.8, because we have to round to the nearest tenth. So 125.8. Okay, and now when we do the same thing for 0, we already know what we're going to get, but let's just plug it in anyway to the calculator. Okay, so we switch that 60 for 0, and we get a value of 500. Okay, so now let's plug in that to these up here. So now we have 125.8 minus 500 divided by 60 minus 0. Okay, let's continue to do the math. Negative 374.2 minus, then we do 60 minus 0, which is 60. Okay, and now we're going to plug in negative 374.2 divided by 60 into our calculators. Negative 6.2 grams per year. Now, the last part of this question asks us to explain what this value means in the given context. So we decided that, based off our calculations, that negative 6.2 grams per year is the average rate of change in grams per year from t equals 0 to t equals 60 years. So that's along here. Okay, what this is saying here is that for every year that passes between 0 and 60 years, the average rate of this change on the graph is expected to go down 6.2 grams each year. Okay, and we can kind of see that as possible based just off of these calculations, right? From 500 to 50, we notice that it goes from the A of t goes from 500 all the way down to 150, and that's just in 50 years. So for every year that passes, going down 6 grams per year is supposed to be a significant drop. And this is also just an average. It is expected to be more in the beginning years. That's why this curve starts off very sharp in the beginning and sorts of plateaus towards the end. And then towards the end, it gets less and less. So that's what that context means from that example. Up next, we're going to have a practice problem just to review. Here's the review question to work on independently. I will now show the answer of it. This is how you would go about solving for this problem. So similar problem, except for we have a choice for this one and there aren't as many parts. Again, using ln and e is important, and also simplifying to the 1000th power. That's what the problem asks for. Okay, so your final answer should be choice 1.